Hello, guys. I'm terribly sorry for being a few minutes late, but as you may know, Willy Carrera, he was a professor in the electrical engineering department, passed away due to COVID-19 a few months ago. I seem to understand that he also was a professor in some of the courses that you may have taken in your career, including one in industrial design, I think, back when you guys were very little and you were in general studies. So we just had a ceremony to honor his memory and to establish a financial fund for supporting students in the biomedical engineering graduate program to attend international events and present at conferences. So I'm just mentioning this because it's important. Okay, there are many things that you guys are going to learn in your education as biomedical engineers, electrical engineers. I think we even have mechatronics engineers among us today. It's a relatively large group this time. It's 32 of you. So there are many things that you may have learned, right? Like chemistry and physics and engineering and writing and theology and whatnot. The one thing that you should probably always remember, though, is that people are not numbers. Okay, so value everybody in your lives, value your family, value your friends, value your classmates, build relationships that really matter. And hopefully for all of us, someday when we are not here anymore, people will remember us in a meaningful way. It's good that you guys are aspiring to be good engineers, but more than that, always aspire to be good people. That's a much more scarce resource nowadays worldwide. You would be surprised. And it's one that we really need, more good people. That being said, welcome to ING 340, which is Introduction to Medical Imaging. And I think all of us are here today, so that's really great. And today we have our first session. So the ones that are familiar with the dynamics of this course, we are going to have a heck of a ride talking about so many different aspects of medical imaging, including ultrasonic imaging, X-ray based imaging, magnetic resonance imaging. We're going to talk a little bit about medical image processing. We are going to have a few invited lecturers throughout the semester, so that's going to be fun too. And hopefully, right, we are going to have a lot of participation from you guys, because that's very useful, and it makes all the difference. Okay, so ask questions, interrupt. It's better that you ask, because medical imaging is a very interesting subject. I guess the same thing can be said about every other subject in your education as engineers with things that are related to biomedical. The interesting thing about it is that we need a little bit of math, we need a little bit of physics, we need a little bit of circuits theory, we need a little bit of algorithms, linear algebra, you name it. There are so many things. And if you don't ask, then it can be more challenging, to keep up. Because again, we cover so many different topics. Okay, so feel free to ask as many questions as you want. There are no dumb questions. Don't ever think that. People that don't ask, they may have the same doubts that you have. They're just afraid, to stand up and say something. So don't ever. Trust me. I mean, it's one of the things I learned throughout my career, just being afraid, because I thought that I was, the ignoramus who didn't know anything. But it turns out that no. And, part of what made my career successful, I guess, is just that ability to don't be afraid when I don't know something and just ask questions. We are going to have, and I think you should be very familiar about that because it's in the syllabus of the course. We are going to have lectures. The lectures are going to be 1 hour on Monday and 2 hours on Thursdays. I don't like to have 3-hour lectures simply because it's overkill. And I don't know. I mean, as much as I find myself entertaining, I don't think I'm entertaining enough that you can be sitting in there, you know, for 3 hours and listening to me talk about things and still be awake. So we have 1 hour on Monday again, 2 hours on Thursdays. The idea again is that you have time to think about the content of the lectures and you can start asking questions and so on and so forth. I'll try to make the materials available before lecture time. Didn't do it today because it's introductory. It's an introductory lecture today, but I will make it available so you can, read, keep up, and you can write down, things that I may be saying that you find interesting. You're going to have the Zoom recordings anyway, so feel free to just send me an email and request some more information if at any point I forget to upload something into the system. So a few things that we need to square out right now. Jandeli Flores sent a very friendly reminder early in the morning about you guys having to choose a representative, or a student representative among yourselves. And that person is going to be in direct contact with myself. Like anything that is simply not working, with the course, that person can explain it to me, or I can, just try to convey messages through him or her to the rest of you. So it's very important to have it, So I guess this is the time where democracy gets in action and you get to elect someone. So I've been told that I need a name before the end of the first 15 minutes of the lecture, and that's going to be 9 minutes or something like that. So does any of you want to volunteer to be a course student representative?
Yes, teacher. I would like to redeem myself, and I also like to be the class representative this time.
Okay. Okay. So do you have a speech prepared? You wanna?
Not really, but I have already experience because of the last semester, and I'm really motivated to understand the course. Last semester, I tried to deep dive into the topics, but I realized that I hadn't enough background. So I'm trying. I have spent like most of the time of my vacations trying to cover up these leakages that I had the last time.
Okay, well, I think
speech.
you did great last semester, but I remember when you told me that you were going to drop the course, and that's okay. But I think you were doing great. But sure, I mean, more than happy to. So I'm just going to, I guess, ask, like, does anybody else want to volunteer? Or maybe we have like an election of some sort, or is everybody okay with Breno being the student representative? So I'm just going to wait for a few seconds of uncomfortable silence in case somebody else wants to volunteer. Okay, so these few seconds of uncomfortable silence served a dual purpose, right? The first one is, well, democracy. The second is, wasn't it really uncomfortable? I mean, it's really uncomfortable, when you're just sitting with a group of people and nobody says anything. So that comes back to ask questions, like, I mean, for me, it's like super uber frustrating, it's like I'm explaining things. It's like, does anybody have a question? Nobody says anything, and it's like, okay, I mean, hopefully you're understanding, but so ask questions, okay? Just be there, show up, because otherwise it feels on my end like I'm just, like teaching and nobody's like paying attention and stuff. So let's get this started. Let me open the material that I need to show to you today. Let me see. Okay. Okay, so this is one of the things I wanted to talk to you about. Okay. Okay. Let me open the other one too. Okay, so here we go. Okay, so let's talk about the course first for a little bit, right? And again, this is ING 340, Introduction to Medical Imaging. For some of you, this is a required course. For some of you, this is an elective course, okay? And just to talk about it, you know, just a little bit of historical background. Initially, this course was merely an elective, right? So it's not mandatory for anybody. Again, that's not the case for biomedical engineers. So the course was designed in a way that appealed to the typical audience of an elective course, meaning here I am assuming that you actually want to learn about medical imaging, right? So the construction of the course, you know, to me is if you have any interest in medical imaging and you want to spend some time, you know, reading about it, working on it, I don't expect you, you know, to jump through hoops to demonstrate that you have like an incredibly amazing knowledge of medical imaging. What I like to do is just to provide tools so you can learn about many different aspects of medical imaging. You become knowledgeable. If this is a path that you want to go, you know, later in your career, then great, you have a good solid foundation. If it's not, then great, and you didn't like, you know, die in the process of trying to learn something that you found interesting to begin with. So that's just basically to say the evaluation of the course, you know, it was supposed to be like, this was supposed to change, I guess, in a little way, because the university is not very happy with the evaluation mode type 4 nowadays for whatever reason. But the evaluation includes class evaluation in the form of quizzes. These are short, so I can talk about each one of these aspects, right? Like last one, the quizzes are very short questions, relatively short questions that are meant to be solved by you in a time span of just, you know, 15, 16 minutes. It's not going to be something as ridiculously easy as write down your name, but you know, it will be something. Typically the quiz will deal, you will have one quiz every week, and it will deal with the topics that we covered in the week before or in the 2 preceding lectures. You know? So if we have them every Monday, for example, then it would cover the contents that we covered the preceding Monday and the preceding Thursday, right? So again, the idea is that, you know, you get to practice, you know, you get to think about some issues that we have discussed in the previous lectures, and you get to do something practical with the things that we're discussing. And it's just not something that, you know, builds and builds upon nothing, because that's not the idea. You're going to have homework. Homeworks are typically for this course is like 3 or 4 homeworks per semester. We don't go beyond that. So typically it's, let's say, 1 for ultrasonic imaging, 1 for X-ray imaging, 1 for MR, and 1 for medical image processing, typically, okay? And these, of course, are meant to be worked on individually. I guess that goes without saying, right? I mean, because quite honestly, I'm based on the assumption, again, that you're here to learn, right? If you're here not to learn, then I guess, sure, I would probably have to tell you, you have to work on this on your own. This has to be, you know, like original, individually worked, you know, solutions to homework. You're not meant to copy from your classmates. But I actually think that the moment that I have to explain those things to you, then this world becomes a very sad place, okay? And I think it's just sad. For me as a professor, for you as students, it's actually kind of insulting if you really think about it, right? You didn't make it to your final year in your career as undergraduate students to even contemplating the fact that you can copy from somebody else. But that being said, I'm obligated still to tell you that in the unlikely event that one of you or some of you are found, copying answers from each other's homeworks or exams or whatnot, then disciplinary actions have to be taken. And again, don't ever do that. That would just be completely stupid, because there's no need. Okay, I mean, the way that this works, and this is something that we're going to talk about right now too. We have these 3 hours of lectures, and additionally, I like to have office hours for my courses. So the other thing that I do is I schedule a 1 hour time slot every week, so we can, sit together. I'm just basically waiting for you guys. And if you have questions, show up and ask. Maybe you're too shy to ask during lecture time. Don't, by the way, again, ask during lecture time. But if you are, then show up for office hours. Or it's not that you're shy, it's just that you're trying to understand that you think you got it, and then you didn't get it, right? And then you go to office hours and ask. Or maybe you just want to ask. It doesn't have to be about, well, in the previous lecture you said something. It can be about, okay, so I want to pursue a career in medical imaging. Like, what do I do? Like, I've been reading about this subject. Do you know about the subject? I mean, can I ask you about this? That's okay. It's a 1 hour time frame to talk about everything medical imaging related. Some things I will know, some things I won't. And when I don't know something, I will simply tell you, but that's a good question. I don't know. Because I don't like students when they BS, and tell me things they don't know. And I don't like to BS people either. But in general, feel free to show up, ask questions. Doesn't have to be about homeworks, doesn't have to be about exams, doesn't have to be about quizzes. But in general, probably has to do something with, either medical imaging or your careers, as biomedical engineers or electrical engineers and whatnot. And the exams are pretty much self-explanatory. This is one thing that I would also defer to you, so you can talk with your course representative, Breno. Typically, the course had, exams. But a format that I prefer, because again, this is a course that is meant to be there for you to learn and have fun, doing something that you like. I think there is nothing more depressing than doing something that you don't like. That sucks, that's like dating someone that you cannot stand, or watch a TV show on Netflix that you find boring. I mean, why would you do that? I mean, there are other things that you can watch. There's other people you can go out with, right? So always do things that you want to do. And for me, the course project, which I offer as an alternative many times, it's basically a literature review, which can be quite challenging, actually. Like, if you ask me, it's a much simpler time commitment to just take exams. Okay, you study and you will know. Okay, like, people have taken courses with me know that if you take the quizzes and if you do the homeworks, there is no way on earth that you're going to fail the exams, because I typically tend to build them in a way that, they lead somewhere. So you will develop the skills that you need to answer the questions from the exam if you just do the work throughout the semester. It's much simpler to actually, I don't know if much simpler, but it's simpler to sit down, take the exam, suck it up, for 2 hours, and you get your 20 out of 20. But typically students are very motivated too, in the sense that they want to work on these literature review projects that allow them to read about something that you want to read. So your evaluation will not be based on what Roberto Lavarello thinks you should be answering, but it's based on something that you find it interesting. You find your passion, right? Maybe it's something that has to do with, I don't know, tomosynthesis or new trends in like tomographic imaging or data-driven, image reconstruction or whatnot. It's your call. Again, your call, and you check it with me, of course. And then you have to deliver a written final report and an oral presentation, so it's a lot of fun too. So those are the two options, again, the conventional exams or work on a literature review project. You get to decide, okay? Like, I'm fine with either one of those. So have fun, talk amongst yourselves. Not right now, because we have other things to talk about. Talk amongst yourselves and let me know which mechanism you prefer for the evaluations. Okay, so that's one thing. So I guess I should also talk about myself, which is something that I personally don't like to do a lot. I can say many things about myself. I am a PUCP graduate. I'm an alumni from this institution. I graduated back in 2000. So I guess I'm the very well definition of a millennial. No, I'm not actually. I'm older than a millennial, but you kind of get the point. I graduated from electrical engineering, which is the reason why I think electrical engineering is like the coolest career in the whole world. But that's me being biased. But then I actually went to grad school and devoted my career to work on biomedical applications of electrical engineering. And hence I got to learn that, engineering and biomedical are like some of the coolest things that you could be doing for your career. I worked for industry before I went into, graduate school and later on academia. From working in industry, I learned that one, I didn't like working in industry, but I got to meet the mother of my daughter, so that was kind of cool. And that's it, I guess. So I attended the University of Illinois, which for the ones that don't know, it is the fourth best school in electrical engineering in the world. It remains to be according to international rankings. Ranking just behind Berkeley, Stanford, and Caltech, and Georgia Tech sometimes, it depends. I got a PhD in electrical engineering from the same institution back in 2009. So you get an idea of how old I am compared to you guys. I'm a full professor at the Department of Engineering starting in 2011. And of the other fun things I've done in my life, I've been an associate editor for the IEEE transactions on biomedical engineering. For those of you that don't know, one, what's an IEEE transactions? Two, what's an associate editor? Well, you can ask me at some other time. I am an associate editor also for the transactions on ultrasonics for electrics and frequency control. I am an associate editor for the transactions on medical imaging. I'm actually the chair of the steering committee for the IEEE transactions on medical imaging. I am the chair of the steering committee for the IEEE International Symposium on Biomedical Imaging. I am a member of the Engineering and Medicine and Biology Society Biomedical Imaging and Image Processing Technical Committee. I am a member of the IEEE Signal Processing, Bioimaging and Signal Processing Technical Committee also. I am a member of the AIUM, that's the American Institute in Ultrasound in Medicine, Post-Echo Quantitative Ultrasound Biomarker Committee, which is just a glorified way of saying that I sit in a committee that tells you how to regulate for the use of ultrasound technology in clinical scanners. I'm pretty sure I've done more things in my life, but there's a reason why I'm mentioning this, and some of you know it already, right? I mean, from this, it may sound like I'm really in love with myself, and I think that I have accomplished a lot of things. I guess objectively speaking, then yeah, sure, probably I have accomplished some things. But the ones that know me, are my close friends or my students, when I tell them this, will know that when I was a student, I consider myself smart. I don't think, it's okay to be like fake modest. It's like Messi saying that he kind of plays soccer. I mean, he does. I consider myself smart, right? Books smart. And that's probably a reason why I spent most of my undergraduate training going to the AELU, which is the sports club in front of the university, for those that know it, hitting on girls, playing with my friends, and wasting my time, 24/7. I never joined a technical society. When I got together to study with my friends, that was literally the day before the exams. We will get together in my house typically, have a steak, like cook steaks and have beers and whatnots. And and that was quad studying. And quite honestly, you know, when I think back, sometimes I just imagine, you know, where my career would be if I had taken the time to study more, to learn more, to find my passion in the things I liked. I was actually very lucky, you know. I got a scholarship when I was an undergraduate student. I graduated, I think, 5th in my class, you know, upon graduation or something like that. I did really well, actually. I got a Fulbright scholarship, and I managed to make it to the US. And that's where I learned, you know, that you can be super smart, but guess what? There's like a million people that are smarter than you. And I remember my first classes, you know, sitting in classrooms with graduates from the MIT, and me thinking like, my God, I mean, they're like geniuses, and I know nothing, you know. And then all of those afternoons, you know, playing basketball or going to the gym and whatnot, all those piled up in my head, and I was just thinking, crap, you know, I should have, you know, been studying more, because I don't remember anything and they remember everything, and I don't know what I'm doing here. I actually remember telling my friends and my family, I'm going back to Peru, you know, I'm so not going to make it here. And I didn't, because of many reasons, which is probably, you know, for another conversation another time. My point being, and remember, this was originally an elective course, right? For everybody, even if this is not an elective for you, for anybody that will spend time learning about this just because you want to, showing up for office hours just because you want to, maybe working on a literature review project because you want to learn. You guys have my utmost respect, and that's not, you know, condescending me. It's for real. You have my utmost respect. And if some of the things I have listed in here sound mildly impressive, I only listed the ones that I think are related to medical imaging. I'm also the program co-chair for this year's EMBC in Mexico. I'm also the Latin American representative at the administrative committee of the EMBS. I'm also a representative at the ADCOM, or the administrative committee of the Ultrasonic Society of the IEEE, among many, many, many other things. So if I could accomplish those things, you can accomplish way more. Trust me, like really, trust me. The only thing that you need is to apply yourselves. So start thinking about that from now. That's another thing, you know, take it from here. We're going to talk about medical imaging nonstop. Don't get me wrong on that. And, you know, most of you, or probably a lot of you already know that. So we'll have time for that, but start planning ahead from now, okay? It may sound like you have a lot of time to make a lot of choices. You may, okay? But start thinking about it seriously. If you want to work on a cool project for your undergraduate thesis, for example, which is, I don't understand why in Peru we have undergraduate thesis, doesn't matter. But if you want to do that, start chasing your professors right now. Do the math, right? I mean, let's say in biomedical engineering, there's like 150 of you getting into the program every year, and you only guys have like 2 professors, right? And if you add the ones that are not fully affiliated with biomedical engineering, for example, then you start adding maybe, you know, just a handful more, maybe 8 or 10. And realistically speaking, nobody has, you know, the manpower to be advising 20 students at the same time. So be smart. Again, you don't want to be the guy that was playing basketball at the ILU and hitting on girls every single day. You want to do that. You want to be the ones that are smart and are thinking, okay, I want to do research on whatever you want to do, right? Clinical engineering, biomechanics, medical imaging, fine. I mean, there are so many interesting people working on those things. Go and talk to them and work on what you want to do. You know, you don't want to graduate, god damn it, you know, and end up, you know, like working for, I don't know, it's interesting to be working on sales, for example, but maybe you don't want to work on sales. You want to develop something, right? And you want to work on, let's say, on Siemens in the United States. Right now, in this memorial for this professor that I was mentioning to you before, One of my former students, who's now working at Siemens in the United States, graduated from the University of North Carolina, which is one of the top 20 biomedical engineering programs in the world, just a few months ago, and she was there. And she's living proof that you can do it, because she actually got into the PhD program in those prestigious universities without getting a master's program here. She graduated an undergrad, applied and got in. You can do it if you just push yourselves, if you just apply yourselves. Don't ever think about this like, I'll have time later on. You may not. I mean, a very sad and cryptic comment I would make, and this would be the final thing before we move on to other things, about this memorial for your professor, Willy Carrera. Nobody, I'm pretty sure he didn't think, 3 weeks before dying that he was going to be dead, by today. Nobody thinks that. If we have learned something from this COVID pandemic, is that everything in life is uncertain. The one thing that is not uncertain is what you guys choose to do, okay? So if you want to accomplish anything, okay, you want to graduate and go to the US and get a job, and whatnot, start talking to your professors. Either me or any other professor that you may have. We'll be more than happy to guide you, because that's part of our job and we like to do it. Otherwise, we wouldn't be working in academia. So of the things that I like to do, of course, most of my career has been spent on medical imaging. That's why I'm here, right? One of the things that we like to do in my laboratory, this is something that one of my former master students did. He's finishing his PhD in the University of Illinois also. And I had the pleasure of being sitting in his preliminary examination a couple of weeks ago. He's doing great, actually. So he was actually studying the problem of constructing this, what we call quantitative imaging maps. And we're going to talk about quantitative imaging later on, right? So it's basically creating images where the pixels give you values of some property of tissues, right? And the state of the art for this particular property, which is attenuation coefficients, tell you that the images that you can get are the ones like in the bottom at the center, which are horrible images that are meant to represent things that are on the bottom right, which look like really nice images, right? And he basically tried to figure out how to construct better maps of this attenuation parameter. And he actually developed a technique that would allow you to reconstruct things like what you can see on the top third column. So the one on the left would be a conventional ultrasonic image. The one on the second column would be what was accomplished with the tools in the state of the art. And what he did was provide tools that would produce something like what you would see in the third column. The fourth column is applying post-processing, like crazy to get the best image that you can get from the state of the art. That would be post-processing, the second column. And even there, that's the best thing that you can get. And the reason why I'm showing this to you again, is Andres, who was the author of this work, is again, he's one of you, okay? And he was a PhD student, right? And he was a master's student back then for me, but he was working in industry for quite some time. And then he thought, I want to go into academia, I want to do something else. And he did. He had all the tools, to reinvent himself, go to one of the best schools in the whole world with a scholarship from the Peruvian government, because if you're going to go to study abroad, that's the best way to do it. You go with a scholarship, okay? If you're going to study, they're going to have to pay you to do it. And that's like the coolest job in the whole world, trust me. So if he can do it, then you can do it too. Always keep that in mind, okay? Like I think one has to be an asshole to just be here and telling you, oh, like these smart people did this. I mean, yeah, he's smart. Yeah, I told you already, I think I'm smart, but I'm pretty sure, lots of you, if not all of you guys, are way smarter than I am, probably than he was. So you can do really great things if you actually like to work on them. He did in vivo, of course, for thyroid nodules, and that's on the bottom, for female breast nodules, or actually tumors, that would be on the top row. We have been looking at, how some of these tools of quantitative ultrasound, in this case, using what's called the backscatter coefficient, which is a parameter that represents reflectivity of the tissues. We have been looking at, how these values will differ from healthy renal allografts to fibrotic or inflamed renal allografts. So for those that you don't know that, when you have end-stage kidney disease, then historically you would go into dialysis, and that kind of blows because it's very difficult, it's very challenging, life expectation is not very good. The other option would be to have a transplant, right, an allograft. And the thing is, once you get the allograft, which to begin with is very difficult to get it, then you want to keep it as much as you can. So the idea here is that you want to develop tools for very early assessing when the allograft is starting to deteriorate. So you can do something about it before it goes bad. Because it was really tough to get one to begin with, it's very unlikely you're going to get a second one. Or if you can, then you want to plan ahead with plenty of time. Okay, and we actually found that looking at the accuracy and the area under the curve, looking into many different factors, the EGFR would be, the state of the art estimated glomerular filtration rate. That's super crappy, when you're trying to find early signs of inflammation or fibrosis. Whereas, the quantitative analysis, which is the one all the way down to the bottom row, did actually much better, with an area under the curve of 0.88, which is much better than 0.53, which, let's be honest, is like flipping a coin. You might as well, that an area under the curve of 0.5 means that literally you just flip a coin, and you would probably do better, and it will be cheaper. That would be nice to see a Siemens branded coin that you can flip. But anyway, we also use some of these techniques for lymph node cancer diagnosis, for example. And these are images of the slope of the backscatter coefficient, a benign nodule that's on the left and a malignant nodule that's on the right. This would be what we call the intercept, benign on the left, malignant on the right. And you see that the colors are different. That's kind of the idea, right? And we did this with a cohort of 20 something, I want to say maybe 24 or 25 volunteers. And we saw that, of course, there's not a perfect separation, right? But if you look at the slope versus, or the intercept versus slope plane, then you can sort of, draw a line and you can separate the benign ones in the bottom right and the malignant ones in the top left. So that was kind of neat because that's something that, is very useful in general if you can produce tools that can quantitatively assess the state of a tissue or state of a disease. A lot of techniques nowadays are being developed not only for diagnosing and detecting diseases, which those two are different things too. So hopefully by the end of this course, you will know the difference between those two. But also for things that are probably even more meaningful, like predicting non-respondents to therapy, right? I had, a very close relative in my family facing and fighting cancer. So I know firsthand how difficult it is. And you probably, lots of you probably were in that situation at some point in your life. Hopefully not, but statistically speaking, probably a few of you at least. And you know that one of the things that's very painful about cancer is that you have, chemotherapy, for example, right? And that's very difficult for the patient, and you suffer from debilitation, from secondary effects. Hair loss, of course, is a aesthetical one that's important, but there are way more, it's very harsh on your body. Same thing with immunotherapy, there are so many things that happen. Like imagine, and it's very likely the case, that you are put into a course of chemo and immunotherapy, and it turns out that you're going to be a non-respondent. Like it turns out that, a couple of months down the road, you're going to have your follow-up CT, and it's going to be worse. It's like, okay, this is not even helping, it's getting worse. You want to catch those on early, so you can, either suggest an alternative course of action, or at least, have a humane, remaining months for a person that's undergoing that horrible set of diseases. So it's very important, again, to identify non-respondents. And non-respondents don't have to be non-respondents for things like, cancer. It can be non-respondents to anything. In our laboratory, we studied, for example, non-respondents to cutaneous leishmaniasis, which is a cutaneous disease, which can actually be lethal if it invades your mucosal layers in the nose and the throat. But in general, it disfigures you. It's an aesthetically challenging disease, and for that one, you also want to catch non-respondents to chemotherapy, because you also have chemotherapy, for that particular disease, because it can metastasize to other places in your body, right? So that's one thing, for example, that's very interesting. For monitoring therapy, for example, right? I mean, you can be having ablation therapy, right? So it can be microwave ablation, it can be ultrasonic ablation. And you're basically cooking tissues, and you want to look in real time which tissues are you cooking, right? And imaging is there for you too. So there are so many applications of imaging beyond the scope of what we typically think of, which is detection and diagnosis of diseases. And it's good that you get to be aware of those kind of things, okay? And in general, when we take a look at medical imaging, we have a time frame that, formally speaking, extends up to the late 1800s, okay? When we have the first picture, that would be in 1895, the first image of the insides of somebody, and that would be the image of a human hand that was collected by William Röntgen. He actually was awarded a Nobel Prize for this discovery. And it actually opened up the doors for the medical community to realize that there was a lot of potential in that. You have to imagine, like, I was helping my daughter the other day with her elementary school homework, right? And she was studying the Paracas culture, right? And you all remember that, right? With the knives and the opening of the skulls and stuff. And I mean, that was medicine for a very long time, right? I mean, you had something inside of you, you had a tumor in your brain, you have a tumor somewhere else in your body, and nobody could look inside of you. I mean, you could have laboratory tests taken so they could sort of infer what was wrong with you. We do that even nowadays, right? For prostate cancer, you have the prostate antigens like the PSA. And if it has elevated values, then you know that very likely you have prostate cancer, but it may not be prostate cancer. It can be prostate hyperplasia or some other benign condition that will also result in elevated PSA values. And you know that prostate cancer is one of the most common types of cancers on the male population in the world anyway, right? So it's good that you know that. So, I mean, for that, again, if you want to do imaging is not that helpful, actually. And you will see a lot of, if you were to do a review, you will see a lot of people still studying on how you can better locate cancerous tumors in the prostate gland. Because nowadays, the standard of care is random biopsies. As painful as that sounds, they literally stick 12 needles in your prostate, which prostate is very tiny, okay? So believe me, I mean, I'm pretty sure that hurts like crazy. Not during the procedure itself, but afterwards, right? But more than it hurting or not, because when you talk about the other, half of the population, the female population, you have mammography, and that involves breast compression. That's imaging too. Well, that's imaging, actually, I should say. And it hurts, right? And so it's not a picnic in the park, but at least it leads you somewhere, right? With random biopsies, the problem is that because it's literally random, you stick so many needles that you think, statistically speaking, you're going to hit a cancerous core if there is a cancerous core, but you may miss it. So it's very sucky. So, I mean, if you want to do something truly awesome for the male population, then go, and work on medical imaging for a good and accurate prostate cancer screening, actually. That would be very helpful. But anyway, there were those kind of tools, right? I mean, you can have pap smears. Of course, you can measure temperature. You can do so many other things. But the idea of actually looking on your insides, and seeing what was happening, that was an an eye-opener. You know, it forever changed and revolutionized the way that we do medicine. I'm pretty sure, again, everybody will say something about that. The people in clinical engineering, the people in biomechanics, all of them will say things like those, right? But it's truly amazing how modern medicine changed because we have medical imaging. It's a revolution that truly changed everything, okay? And during this course, right, we're going to go through that timeline of things, right? And you have ultrasound, and you have CT scans, and you have MRs, and you have ultrasound, and you have so many other developments. And we're going to talk about instrumentation. We're going to talk about the interactions of radiation with tissues. So everything that we're going to do is radiology, okay? Medical imaging also includes things like ocular imaging, let's say with, you know, with visible light. When you want to do fundus imaging, for example, that doesn't fall within the scope of what we do in this course. We deal with the engineering of radiology, meaning radiation interacting with the tissues and producing an image as a result, okay? So those are the ones that we're going to be talking about. We're going to be talking about those interactions. We're going to be talking about the sensors that are used for measuring radiation, you know, or secondary products of the radiation in order to produce an image. We're going to talk about typical clinical applications. We're going to talk about how to play with the images a little bit so you can have a better diagnosis, so on and so forth. Okay, so roughly the topics that we are going to deal with. And I guess at this point, I would like to stop because we're severely running out of time to ask if you have any questions. Again, this was just an introduction to the course, so you know what you can expect. So you get to know me and I get to know you. You get to know how we're going to handle the course. With Breno, Breno, I'm going to send you an email later on so that you can talk with your classmates about the options for the office hours. I think it's going to be a more productive, great use of our time if I just send you some options and you guys get to discuss amongst yourselves, okay, rather than being talking about it right now.
Yeah, that's better.
Cool.
Also,
Okay.
to ask if they would like to have the review or
correct
exams. Yeah,
exactly. Do you guys have any questions about the things that we have been discussing or expectations about the course? Yes, Sergio raised his hand. Go for it.
When we are going to write our reports, are we writing a summary, or because I'm from electrical engineering,
okay,
I don't have the background knowledge to support, for example, analysis like I've read some papers about radiology, but for me alone, but I don't have like sensitivity, PSA. Oh, I don't have the background. So what is going to be the aim of the reports?
Sure. No, I totally understand that. I remember, you know, when I got into the master's program, well, actually got into a PhD program directly, but I still got my master's, you know, from the same university. I remember, you know, taking the only class, see, that sounds very cocky, but it's not. I find this extremely ironic. I mean, as you could have seen, my whole career has been devoted to ultrasound, right? That's what I'm known for globally, you know, for my contributions to ultrasonic imaging. And the one class where I couldn't get an A, right? And the only one that kept me from having a perfect GPA of 4.0 was Fundamentals of Acoustics. And that class had a literature review project. I told you I'm an electrical engineer alumni, right, from PUCP. The one thing that I learned, you know, when I took that class and I had to work on that report is that my training for writing reports and doing literature reviews and things like those from PUCP electrical engineering sucked. Like I thanked electrical engineering PUCP for so many things, but the ability to, you know, conduct literature reviews and learning on topics and be able to cohesively write a report about that, that was certainly not one of them. I still have my report somewhere, you know, it's so much red ink, went into grading it. The one that graded it eventually became my PhD advisor, and we always joked about it. That he said that was probably one of the worst reports that he ever read. And this serves a dual purpose again, right? The first one is, seriously, I mean, you guys can do things much better than I did. And the second one is, don't worry, I understand the feeling, because I was in the same place once. I didn't know how to do it. I didn't know which topic to review. I didn't know with which depth to review. I ended up doing a horrible job, but I got to learn in the process. But we can talk about it. Like if that's the direction you guys want to go for the evaluation, and you want to talk about it, right? And maybe some of you that may be in the same boat, we can talk about during the office hours, for example, about maybe appropriate topics and, how you can direct your literature review. If that's the direction you are going to go, regardless of anything, the next lecture probably would be spending some time talking about literature reviewing, because I would think that would be important, right? I mean, just some basic understanding on how to review the literature, how to read articles, where to find articles, and those kind of things. So let's defer that for after, you guys decide. And if you guys decide to go that way, again, guidelines will be provided. There would be a midterm evaluation and a final evaluation and so on and so forth. So we'll get to work on that. Thank you for the question. Do we have any other questions? Yes, Jose, go for it.
Oh, thanks first for the lecture. It was very interesting. I didn't know many of the things I was reading, and I've read a bit about ultrasound. So I was amazed about some of the results that were shown. I would like to know, I think the question is similar to the previous one, but things about how to start, like studying for the course or where to find information. I think that, as you mentioned, that's going to be approached on the office hours, right?
Yes, but you brought up an interesting topic. So one of the things that I always wanted to have, and we have it starting this semester, was textbooks for your course. Okay, and I know, and let's pretend I didn't say this, but I know that you can find electronic versions of the textbooks in ways that I prefer not to know about. But that's just not the way they should be, right? So there are a couple of textbooks in your library. One of them is, I'm just looking at it, Fundamentals of Medical Imaging. That I think is the second or the third item in the syllabus of your course, which is now posted on the Paideia site of this course. And yes, that you have access via the library proxy to the electronic version of it. So you can just simply grab your copy and that's it. It's unlimited copies for the whole university community. So go ahead and grab it. And you can actually use it as a guideline. Again, I'm going to be posting, material that I developed over the years, but I always found that it's important and interesting to have a textbook that you can refer to, and you can just, read some of the contents too, because it helps to read, when you're unsure, you read, right? So those are resources that starting this semester will be available to you guys. The other textbook would be the principle, I'm just looking at it like from far ahead, Physics of Medical Imaging, which is very interesting to me because it's a different type of textbook, which I enjoy too. It's a textbook that's meant for radiology students, right? Like you get to see that every once in a while, right? You have textbooks that are meant for engineers, to train them into the medical aspects of things. And there are textbooks that are meant for medical students that are supposed to teach them the technical aspects of things. So I always found the latter class of textbooks to be really interesting. And some of the ones I enjoyed just reading, just for fun, were those, where the clinicians would be explaining the physics, the technology. Not because I don't think they can do a good job about it, it's because the focus is very different. So you have those two, to take a read. And of course, you're going to have to study those things with me, with the materials that will be provided every week. But again, I guess the point being, You have textbooks that you can read, you know, and you can find the sections, and I will be telling you, you know, every week, you know, like we're covering this part, and you can refer to this and this section for further details. It's not that you're going to find the exact things I'm talking about. It's just if you want to read more, then you can read this and that section of this book. Okay?
Yeah, thank you.
Sure, no problem. More questions?
Hey teacher.
Hi.
First of all, thanks for the introduction. And I wanted to make kind of a big question, like, is there a groundbreaking technique in regards of radiation, well, radiology? Like, you know, we know about ultrasound and things like that, but is there like a next big thing that's coming up? I'm just curious about that.
Right, and that's been the question, right? I mean, it really depends who you ask, right? For example, we had a very interesting lecture last semester from Jennifer Mueller, who is a researcher that works on electrical impedance tomography. Electrical impedance tomography is basically what the name implies, right? It's tomography, but it images dielectric properties of the tissues, conductivity, the dielectric coefficient, rather than you know, conventional things that you can get in X-ray imaging and whatnot. And one of the areas where this imaging modality, just like, for example, ultrasonic tomography has breast imaging, electrical impedance tomography had thoracic imaging, right, as the application that it was supposed to be good for. So one of the things that we were talking about was, I mean, we're in the context of the COVID-19, right? And thoracic imaging was king during this last couple of years. So that's one thing, for example, in terms of a different modality, right? That's one thing that for example, we thought that it would be interesting. We thought that it would get some exposure. I mean, it did get some limited exposure, but it's always good to know. In terms of radiation, I mean, you have your classic types of radiation, right? And every different modality is working on different types of images that you can get with those types of radiations. But nowadays, I think that the medical imaging community is placing a lot of focus, sadly, on deep learning. Because, right? I mean, I think right now the community is placing a lot of focus on what can we do better that we did sort of okay before, you know, with analytical solutions. Now that we have the ultimate tool in data-driven image reconstruction, which is deep learning, of course, right? So a couple of the projects, which I was very happy that students chose it last semester, had to do with low dose CT imaging, for example, right? Which again, computer tomography with X-rays can give you cancer. You know, it's a lot of radiation. If you can do it with lower amounts of radiation, that's great. With lower amounts of radiation, you have very noisy images. And people attempted to make this work with, you know, filtering image processing schemes, you know, to get rid of the noise. But then all of a sudden, there was deep learning, right? So everybody doing low dose CT nowadays is probably doing it with deep learning. So that's great. In ultrasonic imaging, it was a revolution too, because ultrasound imaging is based on so many assumptions that it's just crazy, right? Even just constructing echographic images. And now all of a sudden, you know, people are attempting, like at Stanford or Johns Hopkins University, we're not talking like baby institutions, right? I mean, like very close friends of mine are working on developing deep learning image reconstructors, not processors, but reconstructors. And that's fascinating, because to me, it's like, okay, I mean, if I were to have a disease, would I trust on a technique that's based on a black box? Probably not. You know, that would be me. Probably a lot of people feel the same way. But as a research tool, you know, it's certainly sparking the interest of many people. And I think that's part of the reason why, you know, the community is so in love with deep learning nowadays, both for reconstruction and processing. And maybe that's the reason why people are finding, ways of constructing images with the same technologies, like the same imaging modalities, the same types of radiation, but very focused on what can these nonlinear algorithms do for you. Like everything in medical imaging is going nonlinear, and that's something that I insist a lot of times in this course. We're going to talk about the fundamentals, right? We're going to talk about the basics of the algorithms, the linear algorithms, the first ones that were derived, and we're going to have fun with that. But when you actually make it to the end of the line, scanners that you have in clinics nowadays, all of them use very, very sophisticated algorithms that go beyond the things that we're going to cover in this introductory course. And that has to do with data-driven imaging reconstruction, that is not using linear methods, but methods that will produce a different outcome depending on the properties of the data that you use to reconstruct the image, and deep learning is key in there. So that I would say probably microwave imaging, electrical properties, like imaging of electrical properties in general, is the one that's probably waiting for that last push, to become a clinical reality. Ultrasonic tomography is getting there too. That's interesting, but it still uses, ultrasonic radiation. And deep learning, certainly it's everywhere. Actually, earlier in the day, I was chatting with a friend of mine about a study in psychology, right? That was demonstrating that prettier people make more money, which is kind of insulting in so many ways, right? But they were doing it with deep learning. And it makes a lot of sense, right? Well, the reason why, and it's out of scope for this, but you can ask me at some more time. Point is, in every single thing that we do, deep learning is there nowadays. It would be actually kind of cool if we can get somebody from Amazon, for example, or Google to give a talk for this course and see if we can make it happen. That would be fun. But anyway, questions? Well, those were a lot of questions. I'm just realizing it's 7:15. And, see, this is what I meant earlier on. If you like what you do, then just time flies by, and we have fun. And that's the goal here. Let's have fun the right way. That doesn't mean it's going to be easy. It just means that you're going to enjoy what we do. Okay, so let's try to make that happen. And we'll see each other on Thursday, and Breno will communicate in between. I'll send you again the time slots that I have available, talk about the course evaluation, and let's resume the conversation. And let's get started with the mathematics of the things that we need to talk about on Thursday. Okay, thank you so much, guys, for being here for this first lecture, and have a nice rest of the day.
Teacher, I have
Yes.
a question. Sorry.
Oh yeah, go for it.
Yeah, about the review. Will the topics of the review will be optional, or like there
will be, if that's the route you go, there would be guidelines,
Okay.
but ultimately you can choose, but the topic has to be run by me.
Okay, so we can propose and you
Correct.
you have to accept it. Okay.
Correct. Exactly.
Thank you.
No problem. And I think, somebody else raising his hand? I think not. Okay, so if there are no more questions, we can wrap it up here. Thank you, guys. Bye.
Thank you, teacher. Goodbye.
Thank you,
Thanks, teacher.
teacher.
Good
Goodbye.
night.
Bye, guys.
Thank you.
Bye.
Hi, teacher. See